In this video, I'm going to be working some Green's theorem examples on multivariable calculus homework 4.6. So this first one here, it's going to ask us to compute a line integral, but using Green's theorem, so that means we need to turn it into a double integral. And I'll just copy in the formula right here. So what we're going to need to do is look at the enclosed region, the region that C encloses, and, write a double integral in terms of that. So I think I'm going to, looking at the region, I'm going to want to integrate with respect to y first, and then with respect to x. With respect to y, okay, I'm going to be going from y equals this line to y equals that curve. So this line looks like y equals 1/3 x. And the curve, well, they told us what that was, right? Y equals 4x minus x squared. Okay. And then x is going to run from 0 to 3. So I know that this integral that I'm interested in computing, now I'm going to have to figure out what nx and ny are. Okay, nx is going to be 2x. So let's see, all right, nx equals 2x. My is going to be 1. So I'm going to be computing the double integral over region R of 2x minus 1 dA, but I know it's going to be dy and then dx. Okay. To be most specific, I'm going to say y is between 1/3 x and 4x minus x squared. I'm going to say x will run from 0 to 3. And these will become my bounds of integration. So on the outside, it's going to be x. The number is always on the outside. And then on the inside will be my y's. That'll be from 1/3 x to 4x minus x squared. And we'll be integrating on 2x minus 1 dy and then dx. Okay. You might look at this and say, oh, I wish I could just anti-differentiate with respect to x first. But this business right here is going to make it that hard. So I think you just want to go ahead with the way we've written it. So we're going to get an antiderivative for this thing with respect to y, which will be just 2x minus 1y. And we'll let y run from 1/3 x up to 4x minus x squared. And we'll be integrating that from 0 to 3. All right, so when we actually distribute this is going to be kind of annoying, but we'll be able to do it. So we'll have 2x minus 1 times, well, just 4x minus x squared minus 1/3 x. I'm going to probably combine the 4x and the 1/3 x, and I'm going to say, all right, 4 minus 1/3 would be 3 2/3. That's going to be 11/3. And then I'm probably going to distribute that. Let's say, all right, 22 over 3x squared. May have been a better way to simplify this, but okay, on the outside I'll have negative 2x to the 3. Inside I'll have negative 11/3 x. And the last two I'll have plus x squared. Okay. So I'm going to add 3 more thirds. That'll be 25/3 x squared. All right, I'm just going to rewrite it. Okay, I'm going to find an antiderivative. Right, x to the third minus 1/2 x to the 4th minus 11 over 6 x to the 2 x runs from 0 to 3. All right. 25 times 27 divided by 9 minus a half of 3 to the 4 is 81. Minus 9 times 11 is 99 over 6. And I mean, I could simplify this farther, but I just don't think that's going to be necessary. You may have even gone with as soon as, like, this spot right here, you might have taken that integral and run it through a calculator and got the same number as me. But that's how we did that. The second one says, find the area of this folio. And they give us equations for the curve in x and y. Okay, I think, I'm not sure how it's coming back to 0, 0. Let me look at this first. All right, so this one, it looks like, obviously, at t equals 0, we're starting off at the origin. And then as t runs towards infinity, it's going to go all the way back to the origin. So in order to find the area of this, what I'm saying is I'm not going to work this on this video. If we want to find the, area, which is the double integral of dA, we can run that, we've got some formulas, right? I think x dy, negative y dx, the one with the half and half. We can do this. But that would require us to integrate from t equals 0 to, up to infinity. And also, I did a little bit of algebra, and basically that x dy thing, or the y dx, it was really unpleasant. And although when you did the half and half formula, it did cancel out a little bit, the anti-differentiation was looking like, just way too much for what we typically do in this class. And especially for, that whole point of these problems is converting double integrals to path integrals to double integrals, not the actual, grinding through and slogging through an improper integral like that. This is one that I'd be happy to work with y'all in class and see if we could find a nice by-hand solution. But for now, I'm just going to leave this one and just not work that in this video. All right, this is a much more old-fashioned Green's theorem problem. Okay. We're going to subject a particle to a force. It's going to move around a closed loop, and we're going to compute the work done using a double integral, right? So we know that the integral over curve C of f dot dr is going to equal the double integral over the enclosed region of nx minus my dA. Okay, we can figure out what those are. Nx is equal to 2x y to the 2, and y equals 2x squared y. That's too bad, those aren't going to cancel off nicely or anything. And so we'll be double integrating over this region 2x y squared minus 2x squared y. Yeah. Okay. Now I think, again, I'm going to be interested in going dy and then dx because, they gave me the equations of these curves in terms of y equals a function of x. So I'm going to say y is between, the curve is on bottom, so that's e to the x squared, and then the horizontal line's on top, and then it'll just be e. X is running from negative 1 to 1. So I'll be wanting to integrate 2x y to the 2 minus 2x to the 2y. With respect to y first, as y runs from e to the x squared up to e, and then as x runs from negative 1 to 1. Okay. Now, I feel like there was something else. Oh, yeah, just, I don't think I'd mentioned it in the first one either, but we definitely want to make sure that our curve is oriented counterclockwise so that we know that it's nx minus my, not the other way around, right? Okay. So that's just something to be aware of. Is that they can ask you Green's theorem questions, with a clockwise orientation. You just have to make sure to make the integral negative. So this is going to go, okay, dx. And then we're going to find an antiderivative with respect to y. So this will be 2/3 x y to the 3 minus 1x squared y to the 2 as y runs from e to the x squared up to e. This will be some, I don't know, maybe stuff will cancel off nicely, and then we'll be integrating that with respect to x. Okay, so we're going to throw in here y equals e. So that's 2/3 e to the 3rd x minus, okay, when I throw in e, I'm going to have x squared, e squared. And then when I plug in, still be integrating this from -1 to 1. Looks like I'm going to need even more room. Okay, and then I'm going to be subtracting, let's see, what is it? But when I plug in e to the x squared for y, that'll be 2/3 x. Okay, when I take e to the x squared and I cube it, I'm going to have e to the 3x squared. Minus x squared, and when I throw in e to the x squared and I squared, I'll have e to the 2x squared. Man, this is not looking good. Let's see, is there anything I can do here? All right. All right, these first two terms are fine, because all I've got is an x and an x squared. This one I can use u substitution on. This one right here, this is really, really upsetting. I'm just going to have to use UDV on that. And I just don't think that's worth it. I would definitely not ask y'all to do that on a quiz or a test or anything. Like, maybe if it was just UDV or if it was just UDU, I would do that for sure. But having you do both in the same integral, that looks really unpleasant. So I'm going to say this is going to be a place where you could type this into your calculator and get yourself a decimal answer. And, you know, it's single integral, so it wouldn't be so bad to type in. You just have to be careful with your typing. But that's how we would compute that path integral as a double integral, is by doing it just like that. All right, here's one that'll maybe work out a little better. We're going to compute the integral of f dot dr. F is that vector field, and C is a circle with radius 4 centered at the origin. I assume we're talking about a counterclockwise orientation. Okay, so I'm going to draw a curve C. All right, and that's got radius 4. All right. So now we're going to say we're probably going to want to use the fact that the path integral is equal to the double integral of nx minus my dA. We're going to go over here and let's see, we're going to take nx, and that's going to be 2x plus 0. My is going to be 1. 2x minus 1 again? That's too bad. Okay, and then this will end up being the double integral over region R. Region R is what I'm going to be highlighting in yellow here. Of 2x minus 1 dA. Okay, it's a circular region, so we know we're going to want to do a polar change of variables. Okay, we're going to want R to run from 0 to 4 and theta to go from 0 to 2 pi. I'm going to just do dr and then d theta. I don't think it'll really matter. Okay, 2x minus 1, x is r cosine theta. And dA is r dr d theta, or r d theta dr if you would prefer that order of integration. I think I'm going to just go with r first. It'll be pretty easy. Okay, this will be the integral from 0 to 2 pi of, let's see, So I was going to actually distribute that in 2r squared cosine theta minus r dr, and then d theta. Okay, now I'll take an antiderivative of, hold on, I was not ready to anti-differentiate. Right, and then I will anti-differentiate this with respect to r, and I'll get 2/3 r to the third cosine theta minus 1/2 r squared, as r runs from 0 to 4. Hopefully that's enough. All right, I'm just going to do this computation right here. And, okay, 4 to the third is 64. 2/3 of 64, that's not going to be a whole number. It's going to be 128 over 3. And then half of 16 is 8. And then when I plug in r equals 0, I'm going to get nothing, so I'll just have that. So now I'm going to be integrating this from 0 to 2 pi. And that'll be, well, when I integrate cosine theta from 0 to 2 pi, I'm going to get 0 because it's going to be sine of 2 pi minus sine of 0, which is going to be 0 minus 0. And so I'm just going to have negative 8 times 2 pi minus 0, so I'll just have negative 16 pi. That's kind of surprising, but, well, who knows? Maybe the vector field is just going against the curve. I don't know what this vector field looks like if I was to plot it. That's really, I think, the missing piece here. All right, number 5. Now, this is a good problem here. So, at first I was really confused about it, like why it had this extra bit hanging over below, but I think you'll see why. It doesn't really matter. So we're going to compute f dotted with dr. C is going to be the blue path that is oriented counterclockwise. It's like, wait a second, I thought we needed to have a closed loop, and we do, right? So what we're going to say is that, no, that's not what I was trying to write. The integral over the closed loop, C, is going to be, f dot dr is equal to the double integral over the enclosed region of nx minus my dA. So I'm going to need to do a little bit of work to enclose this region with a closed curve. So I'm going to come in, I'm going to just draw a little bit more path here. And maybe I'll draw it in pink. Okay. Maybe I'll call that C2. And if I'm calling the blue path C1, then I can say C1 plus C2 is C, and that this integral over the closed curve C, I can write that as the sum of the integral over C1 plus the integral over C2. Okay. And then I know that this one right here, this one's going to be equal to the double integral. Okay, and I'll be able to find that. Actually, it turns out pretty easily. I didn't plate myself quite enough right there, but all right. Okay. And so what I'm going to do is I can, if I want the one of the blue path, then that integral is the one that I'm going to solve for. So I'm going to basically find the double integral over the region and subtract the path integral over just the pink curve, and I'll be able to find the thing that I'm looking for. Right, so first I'm going to find that double integral. So it's actually not going to be so bad. So what we need to do is we need to figure out what nx and my are, and then we're going to see what the deal is. So nx is the derivative of 4x with respect to x, and well, that's just going to be 4. And my, well, there's no y's in that equation, so that's going to be 0, meaning that I'm just computing the double integral over this region of 4dA, and I can factor out that 4 so that maybe it's a little more obvious to you what I'm supposed to do, but this integral, and that just means, well, this amount of area, right? This amount of area inside the region. And, assuming that these are squares, which I think is a reasonable assumption, then that area is going to be 4, and so this double integral is going to be 16. Okay. And then my second step is going to be compute the path integral. Wait, no, just the integral over C2 of f dot dr. Okay. Now I guess I'm going to have to parameterize C, or C2. It looks like that'll be pretty easy. X is always equal to -1. And y starts at -1 and goes up to 0, so I'd say -1 plus t. And then we would let t run from 0 to 1. Yeah, because when t equals 0, r would be at -1, and then when t equals 1, it would be at -1 and 0. Okay, so that's good. All right, now we're going to get f dot dr. So dr is going to be r prime of t dt. So that's going to be 0 and then 1 dt. Okay. F dotted with dr is going to be, x is -1. So this is, all right, probably skipping too many steps. From t equals 0 up to t equals 1, f is x to the third. X is equal to -1, so that's -1 to the third is -1. And then 4x is -4. Dotted with dr is 0 and dt. And so that's going to be the integral from 0 to 1 of -4 dt. And that's going to be equal to -4. Okay. And since the thing I'm looking for is the double integral subtract the path integral came back -4, the double integral is going to be 0, therefore, wait, no, not the double integral, the integral over curve C1, that's going to be 20. So, yeah, I guess that was maybe silly for that to be, should have written those as like, closed loop integrals, but, it's fine. The integral over C1 of f dot dr is going to equal 16 minus -4, which is going to be 20. And that's all for this problem set. This wasn't the best problem set ever, but this was, I had a couple good problems on it. I really liked this one. So thanks for watching.